iC-HausVideo. Integrated Circuits.
Greetings, dear audience. My name is Stefan. I am Sales and Application Engineer for laser products. Today I will present how you get started with the iC-HS 05. With this chip we will generate nanosecond and sub-nanosecond laser pulses from a simple continuous wave laser diode. So let me show you what parts you will need. Here on the table you see all the parts that we are going to need for our evaluation of the iC-HS 05. We have an HS3M high-speed module, a little PCB which is an evaluation board. In this case it's carrying the HS 05 variant of the iC-HS series. This will go onto the host adapter, which then connects it to the outside signals like pulse generator and power supply. In this case I recommend ordering the host adapter together with the heatsink kit, because then you can easily mount it to an optical post or an optical bench system. Last but not least, from iC-HausVideo, the IC384 programming adapter connects the SPI interface of the chip and the HG2D to the computer. Then from an external source you must get a laser diode which is fitting the specifications of the laser driver, to protect the laser diode, earth strap, and to protect our eyes, laser safety goggles which match again the specification of the laser diode. Let's talk about lab equipment. I have compiled a list of requirements and settings we are using today. The photoreceiver and oscilloscope must have at least 10 GHz analog bandwidth. I will use the IC227. This 11 GHz sampling oscilloscope was already covered in our Laser Tools webinar. Power supply and function generator are lab standards. With this, we can now start our first functional test. So let's zoom in on the HG2D. The HG2D is a host adapter for many different high-speed modules and many different laser drivers. So we need to configure it accordingly. Please have a look at its manual to see what options there are. For the iC-HS 05, it's very important to remove here jumper at JP5. This jumper can be used down here at JP8. Also, we are going to supply today a TTL signal using pin P of EN1. Thus, we are not needing here the complex array of jumpers which select LVDS in different modes and TTL modes if we would plug in a special pulse generator here at the channel 1 plug. So as this signal comes externally using pin P, we are going to remove those jumpers. Channel 2 is not at all used with the iC-HS series chips. They only have one trigger channel, so there is no second trigger input needed, so they can also go. Those are the correct jumper settings of the HG2D when you want to evaluate an iC-HS 05 laser driver. So let's plug in the high-speed module carrying the iC-HS 05. And continue directly with the power supply. One for ground and one for the 5 volts. Now we can hook up the ground signal of the function generator, and at the last pin P, the actual signal. Last but not least, we have the programming adapter, which will go into this socket here. Now we have an electrically working setup. Now we can check if the graphical user interface is able to talk to the chip and program it. If you haven't, download the HS1SO GUI from the iC-HausVideo website. Please be reminded that you need to install two things from the zip package. First, the USB driver for the programming adapter, and second, the HS1SO GUI itself. After installation, I plugged in the programming adapter into an USB port, so I will now start the graphical user interface itself. First, it asks us which chip we are currently using. It offers us various types with suffix, which is the chip revision. Today we are having an HS05 connected. So I will select this and click Apply. The main user interface window has on its very top an interface status button. We will click on it to connect to the programming adapter, which then initializes the SPI connection to talk to the iC-HS series IC. Here we have available some configuration and operational mode settings and an ADC readout area. But the main focus of the demonstration later on is going to be the pulse settings here, with a pulse generator for the length of the pulse and the output driver and laser current control columns to influence the laser current and thus the laser power. We also will go through the basic settings because they are individual for each experiment. So when you have a PCB which offers TTL signals, for example, you have to set it to TTL mode in the trigger input, for example. Errors and protection and the hex editor tab are a bit more advanced. We are going to skip them for now. But we will have a look at the status window. You can activate it here or in the menu on the top of the window. So let's click on it. Some status bits are only in memory of the IC, so we have to read them out using the software. Others are signaled at the end check pin. If you're using the HG2D host adapter board, a light emitting diode is connected to it. So whenever one of those indicators here in the software is lit up, you will always have the LED being also on. This is quite nice, so you directly see what's going on. With those information, we can now have a detailed look on how to bootstrap an IC when it first wakes up. For this, I'm going to power cycle the IC and we'll be back in a second. So as soon as we are going to plug in the 5 volts to the IC, the error LED on the HG2D will light up to indicate that it is freshly booted. So let's see if we can make this happen by applying 5 volts to the IC circuit. Okay, this worked. The LED is now on and we can connect to the IC through our programming adapter. So let's check the status. We have some boot up errors, which are normal, and the RAM is freshly initialized, indicating a fresh boot. So let's start with the basic settings. Today our signal for the trigger input is a TTL signal, so we go from LVDS to TTL here. Also, we are going to use the internal pulse generator feature of the iC-HS, which is the main point of the iC-HS. So we are going to enable the PLL for a stable pulse generation. We now have to switch from the configuration mode to go to the operation mode and can now read the status registers once again. The LED goes off and we have successfully bootstrapped our IC. A second click onto the read status shows that we are now ready and can continuously monitor the status of the IC. So we can now go to the pulse setting and check a last thing. The laser enabled since last read indicator will light up whenever incoming trigger pulse is correctly discovered by the iC-HS. As long as the output driver is disabled, we are not detecting anything because we are not dealing with generating a laser pulse yet. So if we enable the laser, this lights up as we have a signal going. Perfect. One remark: at errors and protection tab, there is here the laser was enabled since last read. This should be checked, this box, because otherwise the beam alignment might be difficult, because the bright LED will signal that we have discovered or that we have detected a trigger input, and this might be brighter than the actual laser light. So this is the basic functionality test. If we got this view of the status window, we are pretty okay and confident that it is now time to mount the laser diode and assemble our optical setup with the photoreceiver and the lenses to focus our laser diode onto the receiver. This is the result of assembling an optical setup for measuring sub-nanosecond short laser pulses. We have the 10 GHz bandwidth photoreceiver on the one hand, and on the other hand we have our iC-HS evaluation board with the laser diode soldered to it. The laser beam is beam shaped with one collimating lens and one focusing lens, because the very tiny area of the photoreceiver needs this to be focused very strongly. So we will bring this to a laser safe area, and then we will connect the two wires down here for the voltage supply of the laser circuit. We are going to use 4.5 volts, and then this is the switch which will actually close the circuit of the laser diode. So this is a convenient method to make sure that you have no lasing going on if you toggle this. So that's the overall optical setup. It is coarsely aligned, and if I go now to the laser lab, I will do the fine alignment and then come back to you when we have a signal on our 10, or in our case 11 GHz sampling oscilloscope. The laser was moved to the laser lab. I am now controlling it remotely, so I do not have to wear my safety goggles. I already did the laser beam path alignment so that we are hitting the photodiode and have a nice signal. This took quite some time. So let's go into the bootstrapping of the iC-HS. We connect to it, and then we have to go into the basic settings as the status that reads when we are freshly waking it up is full of errors. We enable the PLL and switch in the trigger input section from LVDS to TTL mode because we have connected a TTL signal to the trigger input. So we can now switch to operation mode to have the PLL take effect. And if we read the status once, most of the errors are gone. We read twice and all of the errors are gone. Perfect, we can work with this setup. I'm going to set the laser current control to 500, which is approximately half of the 1023 that this parameter is capable of. So we will have half of the current from each of the channels. I'm going to activate only 2 channels. Our laser diode is suitable for up to 220 milliamps, and the total would be 250 if I activate all 3 channels, and with deactivating channel 1 I am pretty sure that we are not going over the limit of our laser diode. So let's move this to the right hand side, and now we can enable the actual laser driver stage. We see that we get something here on the oscilloscope. Of course, we want to have it nicely in display so that you can see something. Let's go for a bit more resolution. Yep, here we go. Now, with the maximum pulse length of approximately 5 nanoseconds, we get a 3.9 nanosecond short laser pulse. This is due to an effect of the laser itself. The laser diode has a turn-on delay of about 800 to 900, 1000 picoseconds. So we are losing this current pulse width to some effects of the laser diode. If we want to get a shorter laser pulse, we just select a shorter time span, and if we want to fine-tune it, we can also decrease it in small steps by changing the fine pulse width. Now let's optimize for here the gain switching spike in the very beginning. I will zoom into a bit more. Yeah, this is now only 1.3 nanoseconds short, this pulse. I can further decrease it to below 1 nanosecond. And if I now fine-tune it, we get a nearly perfectly Gaussian shape of just the gain switching. Please note, if we are now change the current, for example, go to 300 in this parameter, the pulse now is completely gone. Let's go back to 500. There it is back again, and now I'm going to decrease it slowly. There is just somewhere the point where there is not enough current going through the laser diode to get it into lasing, even though with a higher current it is possible to get it into lasing. What also is happening while I decrease the current through the laser diode is that it's shifting to the right, so it needs more time to get into lasing. So when you are choosing your settings for your application, please keep in mind that it is more than one variable that influences your laser pulse. For example, if I am here in this regime where I have no pulse visible, I can also get it back by prolonging the pulse. Now we get back into lasing, but with a different current. So those are the options that you have to tailor-made your laser pulse. And let's switch over to my outro moderation. We have reached the end of this demonstration. Thank you for your interest in this iC-HausVideo product. With this easy-to-build setup, you should have a head start in developing your ultra-fast laser pulse application. More details are available on our website. So long and goodbye.
iC-HausVideo. Integrated circuits.